We're going to demonstrate a couple of simple transformer concepts by using some spools of wire and a very limited power supply, and we should be able to understand a little bit about how transformers work. You may see this simplified symbol for a transformer. It has the necessary components, but let's break down what those components are. What we have are two spools of wire, or two coils of wire, and we have an iron core that accents the transfer of the magnetic lines of flux between the two totally independent and isolated coils. If we reposition those and still have an iron core between them, this is what we will have with our example. We're going to take two spools of wire and we're going to put an iron core between the two spools. We have here two brand new spools of wire. They both have 500 feet, so our assumption is that the windings on each of them is reasonably the same. And we have an iron core in the middle of these two, and we have a limited power supply on the one end here, and we put a load on the other end. There's no electrical connection between the two. It's hard to see here, but these are two isolated spools of wire with no interconnection between the two. We have one spool of wire that's connected to the light bulb, one spool of wire that's connected to the power source. To illustrate this concept, when we energize this, we're going to turn the lights off. So you can see there is a very small amount of voltage that makes its way between, that's induced onto this second spool of wire. As you can see, even with the lights off, the light bulb is very, very dim. So we've set our meter up onto this, and we've got it set up here. We're going to turn it on for just a second so that you can see what the voltage output on the secondary side of this simple transformer is. You can see this tops out around 13 volts. In the example, we put 120 volts AC on the primary coil, and we were able to measure, albeit we weren't able to see the light glow very well, we were able to measure 13 volts on the secondary coil. Some principles of transformer theory to review are that voltage and current transfer to the secondary coil via inductance. And in order for us to increase the voltage on the secondary, we need to increase the ratio of secondary turns to primary turns. The higher the turns ratio, the higher the voltage will be on the secondary. We've changed our example a little bit. Now we have a primary coil here, represented by this 500-foot spool, and we have a secondary coil here. So the primary coil is connected to our power supply. The secondary is connected to our load. So we'll energize that and see what. Obviously there's a little bit of a difference between this and the previous example. I've set the meter up similar to what we did with the previous example, and we'll energize it and take a voltage reading. So you can see we're running about 56 volts on this meter. So the next example that we showed had a primary coil of wire, 500 feet of wire, and a secondary coil of wire that was much longer, had many more turns on that coil. We had 500 feet of wire on the first coil of wire and approximately 2,500 feet on the second coil, with our voltage 120 volts on the primary to 56 on the secondary. So in the first example, we had a 500-foot spool in the primary and a 500-foot spool on the secondary, and we were able to measure approximately 13 volts. The second example, we had a 500-foot spool on the primary, a 2,500-foot spool on the secondary, and we measured approximately 56 volts. So our analysis, the second example had approximately 5 times the number of turns, and our second example had approximately 5 times the voltage measured. Assuming 120 volts on the input side, we'll now measure the amperage on the input. Then we can figure out the efficiency. As we look at the efficiency of our rudimentary transformer, we measured 120 volts AC and approximately 44 AC amps on the primary coil, which is, by the way, why it kept tripping our very limited power source. It only held the 44 amps for a very small amount of time. Our secondary coil, we were able to light up a 75-watt lamp with 56 volts. As we attempt to figure out the efficiency of this example, this really elementary transformer and simplified transformer, first of all, we just need to review the power in that we had. We had 120 volts, and we measured 44 amps. So we can calculate that would be approximately 5,280 watts. And that's really why the circuit breaker was tripping so easily, is that we had such a large inrush current there of that 44 amps. The power out, we have to do a little calculation. First of all, it's a 75-watt lamp that's rated 75 watts at 120 volts. So we have to calculate the resistance, and the Ohm's law tells us 120 volts squared divided by 75 watts is 192 ohms resistance for that light bulb. Our secondary power, if you recall, was 56 volts. So we can take the 56 volts squared, divide that by 192 ohms of resistance, and we have approximately 16.33 watts of power on that secondary side, or our power out. So with those two powers, in and power out, we can calculate our efficiency, and that's the ratio of power out divided by power in. So we had 16.33 watts on the output side. If we divide that by the 5,280 watts on the input side, that ratio is 0.003. And you can see that's extremely inefficient for our example. Of course, it was a very simplified transformer. Modern transformers are extremely efficient. They're in the 90+% in the efficiency. So transformers are a very good way for us to change voltages and to transfer power between different systems.